Most exam questions about conjugated dienes boil down to one question. Where does the bromine go? In this video, I'll walk you through a worked example. We'll see how two of these can be eliminated fairly easily, and the one place to look so you can find the right answer in under 10 seconds. If 1, 2, and 1, 4 addition to a conjugated diene feels like a guessing game, you're not alone. The good news, this topic is finite and very pattern-based. In this video, we'll look at the mechanism to show how the different products can form, connect warm and cold temperature to kinetic and thermodynamic control, and predict the major product without memorizing a giant list. Before we get too deep into the mechanism, let's make sure we're talking about the right kind of diene. This is a conjugated diene. A conjugated diene is just two double bonds separated by a single bond. And that pattern, double, single, double, allows the 4 pi electrons to spread out between the 4 atoms. The simplest conjugated system has 4 carbon atoms in a row, with double bonds between carbons 1 and 2, and 3 and 4. Being conjugated allows us to stabilize the pi electrons through resonance. When a reagent like HBr adds, the positive charge resides on carbons 2 and 4. And this is the whole reason why 1, 2, and 1, 4 products even exist. Now we're ready to react with HBr. We've seen reactions of alkenes with HBr before. In a traditional electrophilic addition, a pi bond can react with HBr to form a carbocation intermediate. Either of these conjugated pi bonds could react in this mechanism, but often only one of those pi bonds will lead to the Markovnikov carbocation intermediate. In this case, the carbon 1,2 pi bond will break, the electrons will stay with carbon 1, and carbon 1 will pick up the proton from HBr, kicking out Br- as a leaving group. That allows us to form the tertiary carbocation on carbon number 2, rather than a secondary carbocation on carbon number 3 had we used the other pi bond. Even with conjugated dienes, Markovnikov's rule still wins. The key choice, right off the bat, is where to put the positive charge in the molecule. Following Markovnikov's rule gives us an allylic carbocation, which means it is stabilized by resonance. Notice that in these resonance contributors, the positive charge is always on carbon 2 or carbon 4. Never the carbon in between. Getting Markovnikov's rule right here in step 1 allows us to eliminate 2 of these choices in our answer bank. The bromine can't be on the first carbon. That's the carbon that gets the hydrogen to form Markovnikov carbocation. And if the positive charge is only ever on carbons 2 or 4, the bromine can never end up in the middle. This pair of resonance forms is the engine that drives everything. Each of the positively charged carbons is a place where the Br- could come back and attack. Now we let Br- attack. From our first resonance contributor, Br- will attack the positive charge on carbon number 2, leading to the product with the bromine on carbon 2 and the hydrogen added to carbon 1. That's why we call it the 1,2 addition product. If the bromine interacts with the other resonance contributor, we get the bromine attached to carbon number 4 and the hydrogen attached to carbon number 1. This is why we call this the 1,4 addition product. Notice we only added HBr once, but we get 2 different products because in the resonance contributors, the positive charge is distributed between 2 different carbons. The first thing that we want to say when we look at these 2 products is that the 1,4 product is more stable than the 1,2 product. It has a more substituted double bond. This is the basic mechanism. But now, let's connect it to something that usually shows up on exam, the influence of temperature on the major product. In one version of the reaction, we run the reaction at elevated temperature, either the delta symbol to indicate heat, or a specific temperature like 40 degrees Celsius or something. What you're looking for is anything greater than room temperature. At the other extreme, you're looking for a very cold temperature, usually something like minus 78 degrees Celsius or something. And the question is, which product is major at warm temperature, and which product is the major product at cold temperature? The key connection to make is that the cold product forms faster, while the warm product is more stable. Let's think about this for a second. If we were to magic school bus our way down into the reaction and watch these reagents react with each other, they wouldn't really be this far apart in real life, would they? No, they'd be really close together. So close together, like a bond's length distance away from each other so that the pi electrons can react with the hydrogen. So in real life, the reagents aren't really this far apart, are they? In real life, the hydrogen is directly next to the pi bond it's reacting with. Therefore, when the pi bond reacts with HBr, the Br- isn't really all the way over here in time for the next step. So in that split second after the HBr reacts, the Br- is really right next to the hydrogen it used to be attached to. And this next part is very important. If we keep the reaction temperature low, if we minimize the amount of energy available to the system, tell me, what's faster and easier? For the Br- to attach to the carbocation it's already right next to, or for the Br- to swim all the way around the flask and find the other carbocation all the way on the other side of the molecule. At lower temperatures, when energy is limited, the bromine only has enough energy to react with the carbocation it's already right next to. So the 1,2 product forms under cold conditions, and we call it the kinetic product. Kinetics, think rate, think speed, think whatever can happen the fastest. At cold temperature with limited energy, the fastest thing is to react with the carbocation it's already adjacent to. At higher temperatures, this last step is reversible. The bromine can pop off and form a carbocation. So at warmer temperatures, even though the 1,2 reaction happens faster, it's reversible. And with enough energy, with enough heat, with enough time, we can form the most stable product possible. And the most stable product possible will have the most substituted double bond. The 1,4 product forms under elevated temperature conditions. The 1,4 product we call the thermodynamic product. Thermodynamics, think delta H, think downhill, think stability. The thermodynamic product is the most stable, most substituted alkene. So the fast product at cold temperatures is typically the 1,2 product, and the more stable product at elevated temperatures is typically the 1,4 product. Pause the video, get out a new sheet of paper, see if you can run back through this mechanism from memory. If you can get the carbocation and the resonance forms and the 2 major products down, then matching the temperature labels to the correct product is just an extra tag on the reaction. If this helped, the next thing might be to pair this video with the traditional electrophilic addition to an alkene. That makes this reaction feel like a natural extension and not something completely different you have to memorize. Organic chemistry is not a memorization course, it's a pattern recognition course, and you just added a very important tool to your toolbox. Take a breath, do one more practice problem, and I'll see you in the next video.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.